And Daniel is from the University of Alberta, Department of Earth and Atmospheric Sciences, meeting the demand for lithium to fuel the green energy revolution. Thank you, Daniel.
Great. Thanks so much. And thanks to the organizers for having me among really such a distinguished company. I'm a professor, yes, at the University of Alberta, and one of my lines of research is looking at alternative sources of lithium to, as it says here, fuel the green energy revolution. And that's what I want to talk about this morning. So this is driven primarily by a great increase in the demand for battery metals, among which one of the most important is lithium. And you can see that in two ways. On the left, in terms of projected power demand, so you can see 2022 kind of in the center there, out to the end of the decade. In 2030, there's going to be an exponential growth. And that correlates to projected increases in the demand of these separate metals you see at the right. So this is from 2019, but we have a many-fold increase in lithium in particular that you can see near the bottom. And the issue is that is really well illustrated in this slide here. So we have, again, this projected demand here in terms of lithium itself in tons of lithium. And you can see by the time we get to about 2030, there's a gap between the projected demand and the projected supply. So all the bars, I don't have time to go over them, but they sum up the supply that's online and different versions of supply that are projected to come online. And the issue is that this gap, certainly by 2035, 2040, is going to be pretty gigantic. If we don't start prospecting for other sources beyond the conventional ones, we're going to get to a situation where, well, either the price goes up exponentially or we won't be able to build the products that we need. So what are the conventional sources quickly? There's two, solars, which are salt lakes. And these are primarily located in what's called the Lithium Triangle in South America, other places as well. But the Lithium Triangle borders the countries, or it goes across the borders of the countries of Bolivia, Chile, and Argentina. And so what happens here is there's, again, a salt lake you can think of with a solid crust on the top. You can drill relatively shallow wells and pump up these brines. So a brine is a fluid that has high salinity. And there's lithium in them at fairly high concentration, many hundreds up to a few thousand parts per million. And these brines then are sequentially evaporated into very, well, there's a lot of solar radiation in that region, to isolate the lithium ions and ultimately produce either lithium carbonate or lithium hydroxide, which are the two salts that go into making batteries. The problem here is it's fairly inefficient, so it's about 50% efficiency. It takes many months to over a year to do this process. And these, you can see in the picture here, it's quite environmentally intrusive. The second source is hard rock mines. So these are, many of them are located in the western part of Australia. And we target what are called granitic pegmatites. So these are igneous rocks that can have extremely high, up to single-digit % of lithium in their composition. And it comes with everything you would think about with a hard rock mine. It's intrusive to the environment, being an open pit mine, and it has a fairly big CO2 footprint that's associated primarily or largely with the crushing of the rock to get the lithium out. So we're looking at brines in deep sedimentary basins. So these are down several kilometers in most cases. And these brines that we have, I'm showing the example since we're here in Alberta, and I'm up at the University of Alberta, the Western Canadian Sedimentary Basin. But you can see that in Alberta, we have concentrations that vary from no lithium up to over 100 parts per million lithium. And this would be consistent across British Columbia and also into Saskatchewan, where the concentrations are a little bit higher, in North America in general. And the estimate is that there's many tens of billions of dollars of resource in place, probably actually more, because this is based on an old lithium price. And the upside that I like to point out here is there's already infrastructure that is accessing these sedimentary rocks that are down several kilometers, and that's all the oil and gas wells. So when you produce oil and gas, you produce these brines alongside the oil and gas, and right now it's a waste product. The question being, hey, this infrastructure is in place. These aren't the greatest resources in the world, but can we take this brine and get the lithium out to fill the supply gap that I mentioned before? One of the primary technologies is called direct lithium extraction. And so what you would do, and this is what I'm going to talk about in the few remaining minutes, you get these brines, so they might be petroleum brines, or you might actually drill wells to target areas that have high lithium concentrations. It goes into this direct lithium extraction process, and what that does is selectively strip out that dusting of lithium from the brine and also concentrate it in an acid, which I'll show you in a bit. So you start with a vast volume of brine, you end up with an acidic solution that's much smaller, has a much higher concentration of lithium, and most of the impurities have been removed. And that fluid, which we call the concentrate, can go for further polishing or electrolysis to make the battery salts that go to market. So we are optimizing synthetic minerals to try to recover these lithium from these brines, and that's what I'm going to talk about today. And try to understand and optimize the chemistry of these materials is really the goal of this line of research in my research group. So again, here's a typical brine that I'm going to talk about here. You can see the salinity is 180,000 parts per million. Keep in mind the ocean's 35,000 ppm or so. So again, this is 5-fold, 6-fold the salinity of oceans. And in this we have, in this particular case, just a dusting of lithium, about 40 parts per million. Not a great resource on face, but again, if we can develop a material, maybe this can become an economic resource in Western Canada. So there's many types that are used, but the most popular ones being used in this industry, and I would argue being researched in academia, are manganese oxide. So they're called SPINEL lithium manganese oxide. In this case, nanoparticles. These are synthetic minerals that we're making in the lab. And starting in the upper left of the diagram on the right-hand side, what you do is you take the ingredients of this mineral that you want to synthesize, put them in the presence of lithium, and synthesize, you calcine that mineral. And because lithium is present, you can see the blue kind of spheres in there. Those are lithium ions that are inside of the mineral structure in what are called ion exchange sites. So when you synthesize it, you make vacancies in there that are exactly the size of a lithium ion. What we then do, so now I've got a pile of, it's basically a black or dark brown powder. You take that and you put it into an acid, and it ends up that the only thing of importance in a brine that can fit in those spaces besides lithium is protons, H+, the acidity. So that's what we call the protonation step. As you go on the top from the left to the right, now the protons, those smaller green spheres, are in there. And now you have a powder that you can stick into a brine and selectively recover lithium. So that's what you see on the bottom. We take this material, put it in a brine, and again, you can see all the things being rejected that we don't want. Sodium, magnesium, potassium, and others simply can't get inside the structure. But at the right pH, the lithium will go in there and kick out the protons, and we can load up this very small amount of powder in a very large volume of brine with lithium. Throw all the brine away with all the stuff we don't want, add a little bit of acid, and that will kick the lithium off into this very small volume of acid to make the concentrate. So it's quite clever idea. It's called an ionic sieve. This is what you get. I just want to show you a little bit of kind of specific data, but here's that acid I was talking about. Look, it has a ton of lithium, so it's in millimolar, sorry, but it's about 10 millimolar. Look at sodium, which is a third bar over. Keeping in mind that sodium was present at a concentration 1,000 times higher than lithium when we started. Now it's less than 10% of the concentration of lithium. So the selectivity factors in these are very high. What you see on further on the right is manganese, so that's a problem. That manganese is not coming from the brine, it's coming from the destruction of the sorbent. And succinctly said, this is pretty much the biggest problem in commercializing direct lithium extraction at present. So when we analyze this a little bit further, you can see there's a mineral on the left-hand side. We're using electron microscopy to look at this with a technique called EELS that can actually map what's called the valence state of the manganese. The green on the inside is manganese 4, which is the most oxidized form of manganese. And we make the mineral out of this. And the good thing is it's not soluble, so it ends up that manganese 4 is very insoluble in water. What's happening, you can see on the outside very beautifully in this, we collected this at McMaster, is a red rim which is reduced manganese, either manganese 3 and manganese 2. And this is what happens to the mineral when it's exposed to the brine. We found that the reasons are two. You can see that further over right in the schematic. There's organics in there that can reduce the manganese on the outside, and also hydrogen sulfide, and the brine can do this. And so again, when you get the reduction, when it's in the flowback water or in the brine, you put it in the acid to recover the lithium, and that reduced manganese enters into solution, and this process is called reductive dissolution. So we're trying to inhibit this. One of the most promising, just to finish up here, is coating it. We're doing coating and doping, which is what we're funded to do right now. So we put a thin veneer, in this case of zirconium, on the outside that's porous. It allows lithium and protons in, but hopefully will inhibit the loss of manganese. Starting on the left, you can see the lithium uptake there, and there's three kind of rows there, or columns. There's the bare sorbent, that's the one without any coating. There's 50, which is, you can think of it as a thin coating, and on the far right, 250 is a thicker coating. And the cool thing is, as we raster the thickness of this coating, we don't see any change in lithium uptake. If you go to the right, though, you can see we go from, in this case, about 1.7% loss down to less than 1% loss in each cycle. And so we've reduced the loss by about 50%. We're trying to optimize this because it's critical to be able to reuse these materials at least 100 times for it to be economic. So I would argue there's a lot needed to move this industry forward in Western Canada. I mean, there's got to be support for mining and technology companies, oil and gas operators to get into the business, support for us as researchers, and I would ask, you know, can Canada produce these salts and become a major supplier, or maybe can we even have battery manufacturing in Canada? With that, I'd like to thank all the funding sources, NSERC in particular, and the students who did all this work. Thanks so much.
Thank you very much, Leon.